Yeah, so what we need to know before we study latent heat is the first thing is that there is solid, liquid, gas, and you can take a substance which is solid and you can convert it to liquid and you can convert it back to solid. Similarly for gas to liquid and gas to solid. All right, so these six processes and basically six conversions from one state to another. And all of them can happen at specific temperatures. Obviously, energy is required to change them, and energy is always involved. So, going from solid to liquid, this is how energy increases. So, this is how energy increases. So, solid is at the lowest level of energy in all of them as far as particles are concerned. So, if you're going from solid to liquid or from liquid to gas, you will have to supply more energy. So, we say that these are endothermic processes. So the red arrow shows positive delta H. Delta H means how much energy is taken in. In physics, we usually write it as delta Q, which means Q is basically heat. So both of them are the same thing. Similarly, the blue arrow here, blue arrow shows that energy is given out. So the blue arrow will show that energy is given out, which we show as negative delta H or negative delta Q. So that simply means that energy is being given out. So when you go from solid to liquid, energy is taken in, which means you have to heat that thing to do that. And from liquid to gas, same process. From solid to gas, same process. And the opposite side would be true if we had to convert it to exothermic side. The exothermic side, or we have to go back. So gas has more particles. Gas particles have higher energy. So when you convert them to solid directly, there's massive amount of heat that they need to lose. So they obviously lose that to the surroundings, and that is how the surroundings get heated up when gas cools down. Where do we see this? So for example, you might have seen the backside of a fridge, right? So there's this black whole mesh of a wire there, usually coated in plastic, and there's a black, usually black painted compressor. And what that compressor does is that there's gas inside the refrigerator. I think it was Nefron or something. It varies what brand you have and all that. So there are gases that cool and that provide the cooling effect in refrigeration. So you have a refrigerator, there's a gas inside which has a lot of energy in it. Where did that energy come from? It got that energy from the things that were in the fridge or freezer. Now, obviously, those things, they gave their energy to the gas. So gas expanded, gas had higher energy, and the things cooled down. So why do we use that gas? Because it's good at absorbing heat. Okay, so it has absorbed the heat from the food or whatever is inside the freezer, and it has absorbed heat from it, and now the gas is at a high temperature. So what the compressor does is it compresses the gas, it brings all the particles close together rapidly, and in that way it causes them to lose energy. Because remember that if you compress a gas, it will create a high pressure because they have high energy. So when the compressor does it, it does so by taking that kinetic energy away from them. So not only does it bring them close together, it also takes their kinetic energy away. So when that happens, the gas cools down rapidly. Why? Because you have just converted the gas, you have brought its particles close together, and you've taken their kinetic energy away. This is an exothermic process. So now that energy which the compressor got out of, that compressor has to give that energy to something. Obviously, we remember law of conservation of energy. Energy can neither be created nor destroyed, but it converts from one form to another. So the gas inside has higher energy. Compressor took that energy away from it, so the gas cooled down. And now, where does the compressor send that energy? So the compressor gives that energy through that mesh to the air behind the refrigerator. So that mesh, it is a mesh because it has a higher surface area that way. And that is how the air behind the refrigerator is really hot. It has taken all the energy that was inside through that process. So we can see it over there. What this also means is that if I were to convert a solid to liquid or liquid to gas, that will be endothermic, that will absorb energy, the red arrow. And what that means is that if we had a process by which we were going to melt something, whatever rest of the thing was, it should have lost energy. So that does happen. Imagine you have a block of ice and you hold it in your hand. What happens? Your hand rapidly loses energy, heat energy, to that block of ice. So after a while, you will see that your hand will start to drip and water will start to come out because the ice is melting. But it does get really, really difficult to hold on to that block of ice after a while. Why? Because your hand is rapidly losing energy and our body feels that cold. It does not feel the cold because ice is cold. It feels heat rapidly losing out, which is why we feel cold and we try not to hold that ice for really long. If we do in fact, there comes a point where we have an involuntary reaction to it and we have to let go of that ice after a while. Similarly, if you are somehow uh, in an environment which is really cold, then it is possible that the body starts to shiver, because what the body is doing is body sensing that it's losing heat energy rapidly. So what it tries to do is it creates more kinetic energy. So the chemical energy that we have in the body, it starts to convert to kinetic energy. So we start to shiver. And that shivering is basically the body creating kinetic energy, heat energy, so that it can still restore the temperature of the body. Here's this very interesting experiment that we can do in the lab if we have access to it. So what's happening here? We have dichloromethane in this beaker or can. Dichloromethane is basically a liquid at room temperature, but it has a really low boiling point. And this is a small container having water in it. And obviously there's this block of wood because we want an insulator there. And now there's this straw in there or glass tube. Now here's the thing. If you start to bubble gas into the dichloromethane, okay, so if you blow air into this, what will happen is that you have given energy to it, and because it's a volatile liquid, it's going to evaporate. So what it does is that you keep on doing that, and after a while you will see that the water here will freeze. And that's a very cool, like, it looks really cool when you try to do it, that you have a liquid, you're just bubbling into it, and suddenly the water below it turns to ice. And the reason that happens is that when you are blowing into this, the particles are getting kinetic energy. With that kinetic energy, because it's volatile and there's air in it, it increases the kinetic energy and they start to go out of this dichloromethane liquid. When they try to go out, they obviously take their kinetic energy with them, right? And to evaporate, it needs some energy from the surroundings to do it, because going from liquid to gas is an endothermic process. So what happens is it takes that energy from the surroundings. So it might take it from the can here. It might take it from the liquid itself. So there is obviously dichloromethane has some kinetic energy. So some molecules might take that energy from it and go away. But after a while, it starts to take that energy from this water that is in here. And the water rapidly loses that energy. And so it freezes. And what that means is that now not only is this can and this water block, they're going to stick together really close, but also you can see that it is going away. Okay. So what exactly is evaporation? It is when faster moving particles, the molecules that you have, which are already moving at fast speed, they escape from the surface of the liquid. So what happens is the average speed, because the fast moving things have gone away, the average speed comes down and average kinetic energy of the molecules also decreases. So we can clearly see that the temperature will fall. So and anything that is in contact with that thing will obviously lose energy. So water in here was in contact with this liquid. So water started to lose that energy because evaporation was an endothermic process. We have also talked about it in the past when we talked about why swimmers, when they come out of a pool, they wrap their bodies around with uh, a foil of aluminium or something like that, just to make sure that the rate of evaporation is slowed down. Similarly, we talked about how we can, for example, if you go to a dentist then they usually sometimes not just dentist, even when you are going to a doctor for a simple injection, what they can do is that they can take liquids that evaporate really fast, and they can wrap those, they can dab a cotton, a piece of cotton in that liquid, put that on your skin, and that way your skin feels cold for a while. It goes numb for a while because it acts like a local anesthetic. Because when that liquid touches your body, so let's suppose you're going for an injection, a vaccination or something, and you take a dab of ether, for example. Ether evaporates readily. So you put that on your arm and you rub it a little bit. So there's liquid on your arm. And then when the doctor inserts that injection in there, it doesn't hurt as much because the body has lost energy rapidly from there as the ether evaporated. And that is how it doesn't hurt as much. So pretty simple process, evaporation. And this also happens when we sweat. So if there is a lot of heat or congestion, then we can obviously, if it's very humid, it gets a little difficult to do that, but we can even sweat. And we talked about how that has helped humans rise to the top of the food chain. So yeah, all of this is possible because everything in there that's changing this state is either losing energy or gaining energy. And that energy somehow is difficult or, in fact, impossible to measure with thermometer. We cannot measure this heat, the energy that they've taken in or they've given out during this change of state. We cannot measure it using thermometer. And even if you had a thermometer there, you will not really see any change in the temperature. And that is why the heat exchange that has happened here is hidden. And another word for hidden is latent. So whenever a state changes, the energy difference that happens, the energy that is taken in, the energy that is given out, we cannot measure it using thermometer. And the reason is really simple. When that happens, kinetic energy is not changed. The molecules or the particles, their kinetic energy is not changed. They're still moving at the same speed, but they are overcoming the forces of attraction. And so this energy is used to fight those forces. So it's not that when you were heating it up, the particles were moving faster and all that. Particles were moving exactly at the same speed as they were before, but the forces of attraction that were keeping them close to each other, we were overcoming those forces. And that is why this heat was not being able to be sensed through a thermometer. And that is why it's called latent heat. So what exactly is latent heat? It is the energy required to convert a substance from one state to another. So if you convert it from solid to liquid, we call that thing fusion. And if we convert that thing from liquid to gas, we call that thing vaporization. So latent heat is simply the energy required to change state of something from solid to liquid, solid to gas, liquid to gas. But we obviously give it name depending on how much energy is required. So here's a question. Usually, the latent heat of fusion is less and latent heat of vaporization is high for most things. Why do you think that is? I'll elaborate. Latent heat of fusion is the energy required to convert some solid to liquid. That is usually less than the energy required to convert a liquid to gas. Why do you think that is? Okay, so one answer I received is it takes less energy to overcome the force of attraction in solids than liquids. I thought solids had stronger forces of attraction. Another answer I received it due to arrangement of solid particles compared to liquid particles. Sure, that does play a part. So here's the thing. So think about it like this. You have solid, which is usually drawn like this, and you have liquid, which is usually drawn like this, and you have gas, which is usually drawn like this. The particles have strong forces in there, and the distances, just compare those. So from solid to liquid, the distance isn't as much, but from liquid to gas, the distances are huge. Let me give you an idea of how huge that would be. Let's suppose you have water that is, I'm going to talk about a standard value, which we call 1 mole of water. So let's suppose you have 18 centimeter cube of water. 18 centimeter cube of water is like 2 or 3 gulps. Now, if I were to take that and convert it to gas, then this would be ice, on the other hand, will have a volume of 16.5. Same 18 cm cube. When it was ice, it went from 16.5 to 18 centimeter. I just increased its volume by how much? It was around 1.1%. So it has increased by 10% more. Like there's 10% extra of, so if this was 100% of the volume, this would be 110% of the volume, right? But if I took that liquid and I converted it to this gas, I would have to increase it by 1333%. 1333 with 2 zeros. Yeah. So what's that number? It is 100,000 and 133,000% that I have to increase it. Insane. From solid to gas, solid to liquid, I had to just increase it by 1.1, but from liquid to this gas, I had to increase it by 1333 times. So obviously the energy required to spread particles to that level is huge compared to the energy required to spread particles from solid to liquid. Okay, so you're overcoming the forces. Forces are really strong, sure, but you don't have to just, you just have to overcome them for a little bit. But when you're converting a liquid to a gas, it's huge. All right, so does everybody understand why latent heat of vaporization is more and latent heat of fusion is less? Now, what do you need to know so far? You need to know what latent heat is. You need to know why it is always endothermic. Why do things always absorb it? You need to know why thermometer cannot sense it. And the answer is simple, because it's not about kinetic energy. Thermometer just talks about temperature, which is average kinetic energy. Latent heat is about overcoming the forces. When you overcome the forces, you increase the volume. The change in volume is much higher in gas compared to in liquid. So that's why latent heat of vaporization is usually higher than the latent heat of fusion. And latent heat, where we use it, where we need it, all of that. So let's try to solve a question. So here's a setup. And here's a question. You are hiking in some mountains, okay? And you want to know कि पानी नहीं है आपके पास, and you have been stranded on that godforsaken place for a while. You're very thirsty. And you come across a small puddle of ice cold water, really, really cold. And on one side, you have, obviously, you're surrounded by ice. So the question is, which is smarter? Eating some ice so that it goes into your body and obviously you get water because it will melt definitely, or drinking from that ice cold puddle of water. Which one is the smarter choice? Now, what do you need to know for that? You need to know these things. You just need to know 2 factors here. Yeah, you'll get sick either way, but jaan to bachani hai na. You're in survival mode here. So let's suppose you need 250 cm cube or 250 grams. That should be good enough. It's 1 glass of water. Yeah, that is true. But again, kya kare? Go on, vote. कितने लोग पानी पीना पसंद करेंगे और कितने लोग आइस खाना पसंद करेंगे? I think it's easier to eat the ice. It's difficult to gulp all that ice cold water. Get ice because water could be unhygienic. Yes. Okay. Somebody else, Maheen is saying pani is better. Okay. How do I know for sure? How can we use this data to be sure? We are students of physics. हमें आना चाहिए. Forget about unhygienic for now. Survival mode में चल रहे हैं. So think about it like this. When you eat something, your body temperature is 37 degrees Celsius. Okay. So whenever you, let's suppose you drank some water, which was at 0 degrees Celsius, let's suppose. So you will then have to heat it to 37 degrees Celsius so that it comes to your body temperature. Similarly, ice, let's suppose that was also at 0 degrees Celsius, but this was ice, right? So you will first have to convert it to water at 0 degrees Celsius. And then you will have to heat that to 37 degrees Celsius. So two routes. Either you drink that water, bring it to 37 degrees Celsius so your body can use it. Or you take that ice, first heat it up to water, your body will do that for you. And then bring that to 37 degrees Celsius. So let's try to calculate how much energy that would take. So first of all, I have 250 grams, right? So when I want to heat water and I want to obviously heat water to 37 degrees Celsius, my body will do it for me. So here's the thing. So if you drank water, 250 grams, how much energy you will have to give to that water to make it useful? You are increasing the temperature by 37 degrees Celsius. So that's your delta T. And your mass of water is 250 grams. And the specific heat capacity is 4.2. Why do I need that? Because I need to know how much energy I need to give per gram per degree Celsius. So the total energy I will have to give is 4.2 times 250 times 37. Really simple, right? So 1 degree के फर्क के लिए 4.2 चाहिए, 250 grams के लिए multiply with that, and 37 के लिए उसको भी multiply करते हैं. So I get 39,775 joules that I will have to supply to that one glass of ice cold water to sustain it. Why are we getting different answers? Oh, I put 4.3 in there. My bad. This is not 39,000, it's around 38. Now, let's see, we took ice instead. So somebody else took ice. So first thing that they have to do is they have to convert that to 50 grams of ice. So the mass is still 250 grams. They have to first convert it to water, and then obviously their body will do it, but still, stomach mein hoga. So how much energy they will have to give? So the latent heat of, so obviously this is latent heat, all right? So you have 250 grams, and for 1 gram, you need 340. So for 250 grams, you'll multiply it by that. So the energy, the latent heat that you have to supply is going to be 85,000. That's huge. And on top of it, once it's converted to water, you have to heat it up to 37 degrees Celsius. So, sorry, not 85,000, it's 250 again. And times 37, so that's again 38,500. So now you have to first heat that ice. Your body will do it. It has to first heat that ice to bring it, make it water, and then heat that water to body temperature. And yeah, you're going to spend around 24,000 joules of energy. That is almost 3 times more energy that you could have supplied by just drinking that ice cold water. And if you do that, there's a high chance that this will kill you if you eat ice instead of drinking water. So there you go. Scientifically known survival skills now. Drinking water is better because it uses less energy, and latent heat can be lethal in the wrong setup. All right. So that's it. That's it for latent heat.